March 19, 2001. February 16, 2005. January 12, 2007. And May 15, 2010. These are some of many dates where commercial aircraft have been involved in accidents due to icing. From 1998 to 2007, the NTSB has investigated 50 icing accidents, resulting in 202 fatalities. These statistics came from houseofaviation.com. Today I'm going to teach you about the dangers of aircraft icing. I will include why ice develops on airplanes, what causes iced up airplanes to crash, how icing situations can be avoided, and a very brief summary of the de-icing systems installed on commercial aircraft. First, let me introduce you to why ice develops on airplanes. We all know water can take the shape of 3 different forms: solids, liquids, and gases. Usually when water meets the freezing point, it becomes a solid, just like the ice cubes in your freezer. In the atmosphere, we have a new type of frozen water, and it's called supercooled water. We have an ambient lapse rate, which is how temperature changes as we climb, as we increase altitude. Our ambient lapse rate is 2 degrees per 1,000 feet of elevation. So as you can see, down here below the freezing level, this is the surface, we have liquid water, not a threat. As we climb up here into freezing temperatures, below 15 degrees Celsius, negative 15 degrees Celsius, we have supercooled water. And this is where we have our biggest threat for ice on an airframe. You may ask, why do we even need to climb through these icing layers? Well, what we have going on here is how a wing flies. We have fast-moving air over the top of the airfoil, slow-moving air along the bottom. That's how we create lift, called Bernoulli's principle. We prove it every day. But the more air going over the airfoil, the better the airplane flies. So we like to be up here in this dense air, cold air. Cold air is more dense. Well, up here until we get to above negative 15 degrees Celsius, this really, really dense air is all ice. And it's not a threat to us, because ice doesn't usually stick to ice. So you have an ice cube, they don't stick together. The airplane's cold, the air's cold, the water's ice, so we don't have any threat. This stuff came from Jepson's Flight Instructor's Manual. So we have different types of ice we can get on an airframe. We can get rime ice, clear ice, or mixed ice. Rime ice we'll start to get right down in here. And it's when we're just at the freezing level, it's really light and it kind of flakes off the airplane. We start to get clear ice here. And this is the biggest threat for 2 reasons. It's heavy and it affects our controls the most. We'll talk about that in a minute. Then there's a combination of the 2 different types of ice called mixed ice. So now, why do airplanes crash when they're covered in ice? There are 2 main reasons, like I said. The weight of the ice and how it negatively affects the way the airplane flies. We'll go to a new one here. This is what an airfoil or a wing looks like in normal flight. We have the air going above and below the wing. When we get ice on the leading edge of the wing, we get the air along the bottom not affected. The air over the top, it pushes it up and doesn't stay laminate along with the wing. It doesn't follow the wing. So this becomes turbulent air as well as drag. Now, this is how it negatively affects our airplane, because our control surface is back here. So with no air hitting our control surface, we can't control the airplane. One reason why we crash. The worst case scenario is when an airplane stalls. It's too heavy. We can't hold our elevation unless we pitch up. As we pitch the airplane up, we can get into what's called a stall. So the wing quits flying because of the air going over the top of it. But with the ice on the front of the wing, this happens a lot sooner because it already wants to happen. And this is how a small airplane is really affected by icing. This came from an article from an AOPA magazine. Keep your head in the game. So we like to avoid icing conditions whenever possible, or at least be prepared for them. So we check the weather, we know what's out there, unsuspected things happen, so we like to use our aircraft systems to our advantage. Airplanes have de-icing systems on them. All of your commercial airliners do. They have to. From www.rap.com, I can show you the different aircraft icing systems. First, we have boots. Second, heat. Third, weeping. This is the most common, boots. So you can see that all three of these systems are on the leading edge of the airplane, which is where our ice develops, leading edge of the wing. So the boots expand pneumatically. We use pressure from the engine to expand our boots. When the boots expand, it breaks the ice off from around it. The pilot has 100% control of when this goes on. The heated wing is the most common. That's what you see in most big airplanes, because we have a lot of heat. So we duct that heat into the leading edge of the wing, and we all know that heat melts ice, turns it back into water, where it can leave. A weeping wing is not as common anymore, but there's a bunch of pinholes in the front of the wing, and it leaks out alcohol. The alcohol melts the ice, just like you do on the street in the wintertime. To conclude this lecture about icing on airplanes, I'd like to say that as a pilot, ice is a huge topic. We talk about it all the time. We're constantly learning about it. We learn how to deal with it. And ice is virtually not a factor on an airliner with all these new systems, with all this technology, but it is on small airplanes. The idea of this presentation isn't really to scare you about ice, but to inform you about ice, and how, as a pilot, you can use your knowledge and your systems to make it a safe flight. Do you have any questions? Negative. Good.
I think you covered it all.
Thank you.